So if you've ever heard of a CPU, you've probably heard that it's the brains of the computer or something like that. But what would it actually take to build a CPU from scratch? Well, that's what I'm going to be doing. I'm going to be filming a series of videos where I build a 16-bit computer inspired by Ben Eater's 8-bit computer that he builds in his series of videos. Now, this won't be anywhere near as powerful as the CPU that you're using to watch this video on right now. It's probably going to be similar to something from the 80s or so. So where would you even start with building a CPU? Well, a good place to start is by building the clock. And basically what the clock does is synchronizes the whole computer and keep it in time. So if we want to build a clock module for the computer, a really good way to go about that is by using the 555 timer, the 555 timer, which is what is inside this green box. Inside this green box is what makes up a 555 timer, and everything outside of the green box is just additional hardware that's been added to actually get the clock pulse from it. So there's a 1 microfarad capacitor connected from ground to pin 6, and pin 6s and 2 are just directly connected to each other, and in between pin 6 and 7 there's a 100k resistor, and in between pin 7 and 5 volts there's a 1k resistor, and connected to pin 3 is just a LED with a 220 ohm current limiting resistor, and that's just connected to ground at the end. And so the names for these is pin 1 is ground, pin 2 is trigger, pin 3 is output, pin 4 is reset, pin 5 is control voltage, pin 6 is threshold, pin 7 is discharge, and pin 8 is just VCC. And so I'll run over how this IC works. So first, let's look at these 3 5k resistors that are set up in series directly from VCC to ground. So these are set up in series, so they create a voltage divider, and since they all have equal values, they just cut the voltage in thirds. So the first point here, that's going to be 1.67 volts because you have 5 volts here, and a third of 5 is 1.67. Then at this next point you're going to have 2/3 of 5 volts, so that you're going to have 3.33 volts, and then these just become inputs for these comparators. And basically what comparators are, if this plus terminal is higher, if the voltage is higher than the negative terminal, then this comparator is going to output 5 volts. If the negative is higher, then it's going to output 0 volts, and then these two comparators feed into this SR latch. And so how an SR latch works is when the set goes high, the Q goes high, and that latches in, so even if the set goes low again, the Q will stay high until the reset then goes high, and then the Q will turn off. And then this is inverted Q, so the Q with the line over it, and that's just whatever the Q is, and so if the Q is high, that the inverted Q will be low. So now I've covered all the hardware for this Astable setup for this chip. I'm going to go over what it looks like when this thing is powered on. So as soon as it's powered on, you got VCC connected straight to ground here. So here. So you're going to have current running through here. And since this is connected here, you're going to have current running through here. And so let's just say that all of this is 0 volts because it's just been turned on, there's no power here. So instantly you can have 1.67 volts here and 0 volts here because pin 2 is connected here, and this is just connected to 0 volts because we just powered it on. 1.67 is higher than 0, so you're going to have current flowing here into the set pin of the comparator, the SR latch, and so the Q pin for the output is gonna turn on, and the LED is gonna turn on. And so almost instantly you're gonna have this LED on. Now let's look at what's gonna happen over here. So you just powered it on, it's gonna be 0 volts, but now you're gonna have current flowing through here. You're gonna start to have current flowing through here. And so this capacitor is going to charge up, so it's going to slowly charge up and the voltage is going to rise. You have pins 2 and 6 connected here, so as the voltage rises here, the voltage for these pins will rise too, and these pins are directly connected to the comparators, and so you're going to have current flowing through here. So the voltage is slowly rising up like that, and then it hits 1.67 volts. That's a bad 6. 1.67 volts. Once it gets higher than 1.67 volts, then this positive input will no longer be higher than the negative. So this set pin for the SR latch is going to turn off. So I'll put an X there for it turning off. But the voltage here is still going to be rising. So it's going to be rising, and then it's going to hit 3.33 volts. And so once it hits 3.33 volts, it's quickly going to get larger than 3.33 volts. And since you have pin 6 directly connected to that 3.33 volts, and that's connected to the comparator, the positive end of the comparator, once it becomes larger than this 3.33 volts, you're going to have current flowing through here, because again, that's how comparators work. And so it's going to reset the SR latch. So you're not going to actually have current flowing through here, and then you're not going to have this LED lighting up anymore. This LED's going to be turned off. But this not Q output, the inverted Q output, is going to turn on, and that comes to this transistor. And so you're going to have current flowing into the base of the transistor, and so that's going to open up the collector emitter passage. So you have the collector connected to pin 7, and pin 7 is in between the 100k and 1k resistor. Okay, so I got rid of a lot of the arrows because we're about to start, we're getting into the next cycle. Actually, I'll get this capacitor graph sort of thing back. Okay, so you have this transistor turned on, and the emitter is directly connected to ground, and the collector is connected to this area here, which is connected to pin 7. So current can start flowing through here directly to ground. So this capacitor, that means this capacitor can start discharging through here down to ground. And so what this will look like is that it's going to drop below 3.33 volts, so this reset's going to go low, which isn't going to do anything because it's already latched in, but then the capacitor voltage is going to drop below 1.67 volts, so that's going to set the latch, and so not Q is going to go low. So that's all going to go low. The set's going to go high. Q is going to go high. The LED is going to turn on. And since there's no open path to ground, like directly through the transistor, it's going to have to flow through the capacitor. And the capacitor is going to start charging up again. And so all of this is going to be on, and it's going to rise above 1.67 volts, that's gonna make this set go low, and then it's gonna rise above 3.33 volts, the reset's gonna go high, and it's all just gonna do it all over again in a continuous loop with this LED output turning on and off. As this rises, the output is going to be high. So this is 5 volts here, but then as it discharges and goes below 1.67 volts, it's just going to drop instantly. And then as it charges up again and goes above 3.33 volts, it's going to jump up to 5 volts again. So here is 0 volts, that's there. So it's just going to create this square pulse wave. It's going to be pulsing on and off in a square shape. So that's what it's going to look like. And one pin that I didn't really actually talk about much was pin 4, which is connected to 5 volts. That's a reset pin, and I've just connected that to 5 volts so it doesn't keep resetting. And it's actually active low, so you have to tie it high to stop it from constantly resetting. So that's why it's tied high. So now I'm gonna build this on a breadboard. So I'll plug in the 555 timer, plug in 5 volts to pin 8 and ground to pin 1. I'll also plug 5 volts into pin 4 into the reset pin. And now I'll plug in a 1 kilo ohm resistor in from 5 volts to pin 7. And I'll connect a 100k ohm resistor from pin 7 to pin 6. And now I can connect pin 6 to pin 2. I'll plug in a 1 microfarad capacitor from pin 2 to ground. Now I connect an LED to pin 3 and just plug in a 220 ohm current limiting resistor from the LED to ground. And now I can plug in power to the breadboard and turn it on. It seemed there's something loose. Yeah, it was just one of the resistors were loose, and that's why I'm not building on breadboards and I'm making it on a PCB, because stuff can come loose really easy on a breadboard. But yeah, it looks like it's working fine. I'm getting a nice flashing pulse. Looks like it's doing everything right. So yeah. So now we can look at the maths behind all this and see why it's flashing at the speed it is. And there's a few different formulas to find out different things. There's TH that tells you how long the output spends high. There's TL to tell you how long the output spends low. But there's another formula that will be probably more useful to us, which is the period formula, and that tells you how long one cycle takes. So now we can write this all out. So period equals 0.693, and then that's multiplied by RA, or open brackets, plus 2RB, and then that's just times by the capacitance. So that is 0.693 times, and the value of RA is 1000 ohms, plus 2 times 100,000 ohms. And then you also multiply by the capacitance, which is 0.000001 farads. So now we can plug all of this into a calculator. So we need to start off with what was in the brackets first. So I'm going to start off with 2 times 100,000. That's 100,000. That equals 200,000 then plus 1000, 201,000, and then times by the capacitance, which was 0.000001 farads. That equals 0.201, and then multiply that by the 0.693, and that equals 0.139293, and so that's how long each cycle should take. So I got the circuit hooked up to an oscilloscope now, where the yellow line is the output and the blue one is the capacitor voltage, and you can see the output voltage going up and down and up and down, and the capacitor voltage rising and then discharging and then charging and then discharging. And you might notice that the output is spending more time high than it's spending low, and that's because it has to charge through 100,001 ohms, because there's a 1000 kilo ohm resistor and a 100,000 ohm resistor, but when it's discharging it only has to discharge through the 100k resistor. And you can see here that the highest voltage the capacitor is charging to is in 3.33 volts, and the minimum is in 1.67, and the output voltage is above 5 volts, where it should really be around 3.5 to 4 volts for if I'm supplying 5 volts, and we'll look at that later, what's happening there. And you can see the period isn't exactly what we calculated, but it's pretty close, and the reason why it isn't exact is most likely just because the resistors aren't exactly 100 kiloohm or 1 kiloohm, and the capacitor isn't exactly 1 microfarad, so it changes a bit, but it's pretty good. Another thing we can do is zoom right in on this transition from low to high, and you can see it's actually not anywhere near as much noise as I expected, but I can put a 0.1 microfarad capacitor in between power and ground just to smooth things out in case there is some noise or something like that. But yeah, there's surprisingly not as much noise as I expected, so I'll chuck that in. And another thing that the manufacturer recommends is putting a 0.1 microfarad capacitor between pin 5 and ground. I didn't notice any difference with it just because the output I had was already so clean, but I'll just chuck it in anyway. So if we want to be able to change the speed of the clock, a really good way to do that is by changing the value of one of the resistors, and this will change the amount of time it takes for the capacitor to charge and discharge, which will then change the frequency of the output. So if I change the 100k resistor with a 1 mega ohm potentiometer, that'll do fine, because you'll be able to go from 1 mega ohms, which will be really slow pulse because the capacitor takes a lot longer to charge and discharge through 1 mega ohms, or you can change it to near 0 ohms, which will take the capacitor no time to charge and discharge. So I'll take out the 100 kilo ohm resistor and replace it with a 1 mega ohm potentiometer, and I bent one of the legs of the potentiometer just because I don't need it here. So you can see if I get a screwdriver and change the resistance of the potentiometer one way, it'll lower the frequency of the output, and if I turn it the other way, it'll output a higher frequency. So before we noticed that we weren't getting the right output voltage, and the voltage that the capacitor was charging to and discharging to wasn't quite right, and that has something to do with the power supply that I'm using. Output's 9 volts, and that power supply that plugs into the wall leads into this device that plugs into the breadboard, and I looked it up, and I should be able to supply up to 12 volts with this and it still give a 5 volt output. So I think it's down to this thing that plugs into the breadboard that isn't quite working right. And what I'm gonna do to solve this is just use this USB adapter that plugs into the wall, and I've also got a USB cable that I've soldered to male headers to power and ground, so I can replace that now. And I'm also going to need 2 jumper leads from the top power rail to the bottom power rail, because before with that power supply I was just using it connected to both power rails, but this one doesn't. But when I plug it in, you can see there's crazy amounts of noise, and that's because of my ring light. When I turn my ring light off, all the noise goes away, but when I turn it back on, it comes back, and that's because my ring light is plugged into the same USB adapter. So that'll all work fine, just as long as I don't use the same adapter for my ring light and a computer. Now I've covered everything I need to on this circuit, and I can start building a proper schematic for the PCB on Easy EDA. Okay, so I got Easy EDA open, and first I'm just going to grab all the parts I need for the circuit. Okay, I'll just zoom in on this a bit. I'm going to need to duplicate the resistors because I need 3 of them. So now I got the 3 resistors I need. I'm going to rotate that to how I had it drawn, and I'll hook up 5 volts and ground to VCC and ground on the pins, and I also gotta hook up VCC to reset. I'll get these out of the way. Okay, so first I'll get this capacitor where it needs to go, like that. That's just connected directly to ground. I'll hook up the LED, just move that out of the way. Hook that up to the current limiting resistor and to ground. I'll connect the 0.01 nanofarad capacitor. I'll connect pin 6 to pin 2, like that. I'll connect this resistor, I'll put that in a more convenient spot. Do that. I need to connect that to pin. Connect that to pin 7. The potentiometer. Yeah, that's a good spot for that. And then I need to connect it to pin 6. That's a whole schematic of the Astable 555 timer. So thanks for watching.